So let's just start right away. So today we talk about how to reduce cost and lead time in metalworking with on-demand jigs and fixture. So I'm going to be moderating this chat. My name is Juliette Combe. I am a product application engineer at Formlabs. So I conduct research for the product team in manufacturing applications, so usually in collaboration with industry experts. And today I'm hosting this webinar with a guest speaker. So Bradley Matthews, that can introduce yourself.
Yes, I'm Brad. I'm the owner and founder of the Factory Amsterdam. We do contract manufacturing of metal and plastic parts. And I've been in manufacturing for about 15 years now, doing both additive and CNC machining work.
Perfect. Thanks, Brad, and welcome. And thanks for joining us today. All right, so let's just share the agenda. Today, I'm going to start with a quick introduction about giving some context and why 3D printing jig and fixture is useful in metalworking. I will just give the quick workflow and guidelines for 3D printing. And then Brad is going to share some insight about his activities with 3D printing. And then we will have a Q&A session at the end. So for the Q&A session, please use the Q&A button. Don't use the chat because we cannot track all the questions through chat, but we can track everything via Q&A. And we will also address the questions that are upvoted first. So the one that are the most popular questions, we will look at them first. All right. I first want to start with some quick question to understand a bit who's the audience today. So you will have a poll that pops up on your window, on your screen, just to understand a bit if you are, if you're familiar already with 3D printing, if you're familiar with metalworking, and what are you looking for from the webinar today? So you have 3 questions. You can just answer directly in the poll. I'm just going to leave a few seconds for everyone to answer. All right. Interesting. So, all right, I'm just going to end the poll and also share the results. So to understand a bit who's the audience, so most people today, 60% are already using Formlabs printer, but we also have some people that are non-Formlabs printer and a few people that are not currently using 3D printing. And in terms of metalworking operation, a lot of people are doing CNC machining, welding, finishing processes. So it's quite diverse actually today. And what kind of part are you interested in 3D printing for metalworking? We see that there are a lot of people interested in work holding for machining, work holding for welding, but also press and forming tool, assembly fixture. Yeah, a lot of different use cases. So that's great. I think we're going to have a lot of interesting discussions. All right, thanks a lot for sharing that. I'm just going to close the poll. All right, someone I think is raising a hand. Good. All right, so let's start now. I will first start with a quick intro on the topic. So jig and fixture are used to increase precision, efficiency, and safety in manufacturing operations. So First, a quick reminder, what is metalworking? So it's a range of processes for shaping and forming metal to produce metal component. And usually it involves some sort of force and temperature, and it's quite demanding process. So actually using tools for metalworking is very important to increase precision and safety and repeatability in the process. So it's tool making in metalworking is very critical for these concerns. Typically, they are made with traditional manufacturing process by CNC machining or sometimes manually in assembly, and they are made out of metal. So this can actually limit in some ways the flexibility of making tools for jigs and fixture because it can take weeks to order a CNC machine tool or even to have a free spot on your CNC machine if you have that in-house. And depending on the complexity of the design, it can be very expensive as well. So this can be very limiting to actually produce fast tooling and to produce also to iterate on the design and produce jigs and fixture very quickly. So for metal workers that are looking to produce a very quick jig and fixture, there is a bit of a gap. So this is where 3D printing enters and can help close this gap for making jig and fixture quickly. So by 3D printing jig and fixture, you can actually reduce cost and lead times by up to 90%. So we have a few different case studies and user feedback on cost analysis for that. So it's actually quite valuable in terms of cost and time reduction. It also allow on-demand production and to actually move from a physical to a digital inventory. So you don't need to store jigs and fixture like metal jig and fixture in-house. You can just have a digital inventory. It increased design freedom and customization, so you can move to much more organic shape and curved shape that are difficult to manufacture with traditional manufacturing methods. You can introduce customization much more economically. And then it allows for more precision and repeatability for, in the case of producing metal jig and fixture, for example, a manual jig and fixture. With 3D printing, you can actually have much more repeatability and precision. And finally, you can also incorporate ergonomic features, and you can also reduce weight from moving to a metal jig to 3D printed plastic jigs. So that's for the benefits of using 3D printed jig and fixture. Now let's look at quickly the workflow and the guidelines. I just want to give a quick intro, but then Brad will explain a bit more about his own experience about 3D printed jig and fixture afterwards. So at Formlabs, we design, manufacture professional 3D printer. So we have two product lines, SLA and SLS, which are both suitable for 3D printing jigs and fixtures. I will, in the next slide, I will show how to choose which technology. But they are both suitable for the workspace, for the machine shop, and they are very easy to integrate in your current process without much disruption. And they come with different range of materials. So now in SLA, you have a very broad range of material with different material property. And in SLS, you have also a lot of different range of powders that are actually nylon powders, mostly, but not only, that can actually be very suitable for the industrial applications. And we also have a full ecosystem with the hardware, the accessories, the post-processing tools, and so on. So the first step for 3D printing jigs and fixture is to decide what technology to use. Obviously, today we look at, we have two main core technology, SLA and SLS. At Formlabs, we recommend using SLS so SLS is a selective laser sintering process. So it's a powder-based 3D printing process. And we have the Fuse series that is powered by SLS. And I will recommend using this technology if you want to print strong, durable, and heavy-duty tools. So that will be parts that are used repeatedly or needs to be very durable. Also, usually as default part, a lot of our customers are using nylon 12 powders because it's very versatile. So it's really great choice for many different applications. It's chemical resistant and environmental stable, sorry. So that will be critical for using machining fixture. We're going to see some example a bit later on. And it's also lightweight compared to metal, and you can actually build quite complex design because the part, when being printed, it actually sets on the powder bed, which means that you can really have complex geometry without using supports. And finally, SLS printing usually is quite cost efficient for large volumes. On the other hand, we are not going to focus on that today, but I still want to mention that SLA, so stereolithography technology with the Form 4 and Form 4L is also a good choice for 3D printing jigs and fixture. But in that case, that will be more for precise, smooth, and detailed tools, sometimes also with ergonomic features. That will be also in the case where you want to choose technology that has a wide range of material properties. So, for example, high temperature resistant or ESD safe materials. We also have silicone materials. So this is a good criteria to take into account when choosing this. And for one-offs and low volume production, it's very fast and easy, and it also has a lower entry price point. So here's the overview of both technologies. And once you choose your technology, then the workflow is pretty simple. You design your part in your CAD. You upload it in the print preparation software. So that's the first step. And then you prepare your print, send it to the printer, just press print. And then after, you just need to process either with, if you choose the Fuse series, then you have the blast, the sift and the blast, or if you choose the Form series, then you just have to wash in IPA and post-cure. And then once you have your part, usually you don't have to do any additional post-treatment. You can just deploy in your process. And finally, I just wanted to mention a few different cases. So we have cases for machining fixtures. So that's a big part of the example that Brad is going to talk about today. But we also have some case from welding fixture, for sheet metal forming dies, assembly fixture, robot grippers. So a lot of different application in jig fixture for manufacturing in general. I forgot to mention at the beginning of the webinar, but we're going to have a white paper that will show the different case that I mentioned. And we also have a lot of different assets on those parts and case study. So you will receive that afterwards as a follow-up of the webinar. All right, so that's for the quick presentation and introduction about this topic. Now I really want to give the floor to Brad, who's going to share some insight from working with 3D printing in his CNC machine shop.
Thanks, Juliet. So as she mentioned, I'm going to be talking about my use of SLS printing in my shop, which is called the Factory Amsterdam. We started out in Amsterdam, New York, hence the name. And we specialize currently in production CNC turning. So as you see in the picture there, I've got a dual spindle Y-axis lathe that is bar fed. So it takes sections of round stock, runs them in through the main spindle, does a bunch of machining operations, transfers it to the sub spindle on the right side, finishes the backside and spits it out. And that's done all in one operation. So my shop is primarily just me. Occasionally I have a couple interns from a local college, but I'm doing most of the work here just about every day. So streamlining my operations is critical to my business outcomes. In addition to machining, we do offer SLS 3D printing, primarily in nylon 12, as a secondary service, but the major focus of the business is on machining. So we'll get started by taking a look at probably my favorite application of the fuses so far, and that's these collet pads for the lathe. So when you're holding a part in the subspindle, if it's already been finished on one side, you don't always have a nice smooth diameter to work with. Sometimes you've got a complex contour if it's been milled. And that can introduce a lot of challenges with traditional work holding solutions. So if you look at something like the collet chuck that's shown in this picture, you've got in this case, you've got a steel master collet that holds collet pads. And those can be plastic, they can be steel, they can be aluminum. And traditionally, these are hardened tool steel collet pads. So they're little inserts that you pop into that master collet in order to change the diameter that you're gripping on, or the shape or whatever. And they sell off-the-shelf machinable options in softer steels and aluminum and even in nylon. But these can be quite expensive, and they even pale in expense compared to using just a solid collet. So a traditional tool steel collet for this chuck is on the order of $300 to $500 per size, and each size can only clamp in about a 1 millimeter range. So you can imagine that if you're doing a variety of parts, you need a lot of collets, and that gets really expensive really quickly. Now, I'd like to make the point here that these aren't a perfect solution to everything, these printed collet pads, but where they do work, the cost savings are tremendous. You can see in the table here that a typical off-the-shelf collet pad for this master collet is around $150 a set. And if you're buying machinable ones, they're often special ordered, so it adds time to delivery up to a month, sometimes even more if they're not in stock. Where with the fuses, I can print these same parts in nylon and have them the next day. They cost me $7 a set in powder. So I don't have to worry about consuming really expensive work holding components every time I set up a part. Because when you're using inserts like these, they have to be skim cut in the machine in order to guarantee concentricity with the spindle. And in a lot of cases, that is crucial. Now for these plastic collet pads, they do have a little bit of give to them because they are plastic, and that can sometimes work in your favor. Sometimes it can introduce a little bit of run out into the part, and that can produce error in your part geometry. But if you go to the next slide, you can see I've been successful at holding some very large parts with these. So this is a piece of 2-inch steel bar that's about a foot long overall, and it's hanging out, 8 or 10 inches from the chuck. That's not a small amount of cutting forces when you're working on the end there. And at the same time, these parts are exposed to coolant, which is a water-soluble oil, and that does attack a lot of plastics, but the nylon can handle it. You can have very high spindle speeds involved. You've got high radial clamping forces. And in some cases, I'm using these collet pads on production parts for thousands of parts, hundreds of hours of production. And actually right now the machine's running in the background with these collet pads in it. It's been going for the last week. And in that sort of situation, I treat them as a consumable. but other machinable solutions for these collets are also consumables. And the cost reduction here is really tremendous. So up next, we have a video of what the machine's doing, and I'll talk through it. Um, so this is showing the production parts that I'm running right now. They're small aluminum components that have a flange. It's about 6 millimeters thick. And that's really tricky to clamp onto, especially when it's not totally round. So this has a machine profile in it, and you'll see it in a second. So right now the sub spindle's coming in, it's grabbing onto that part, and the cutoff tool's gonna cut the part off the bar. When that completes, it backs up a little bit, advances the bar stock, and then it's gonna go back to its home position to work on the backside. So there it goes. And my apologies for the shaky video. I was trying not to get soaked with the coolant here. So right now it's coming in to face off the backside of the part. And in this case, that's the only operation that needs to be done on the backside, and I consider that ideal for these collets. This is a cosmetic only face, so the accuracy isn't super critical. So as the collet pads wear over time, um, the exact parallelism of the front and back faces, it isn't as crucial as it might be for other parts. So, I'm still holding parallelism and concentricity within about 1/1000th of an inch or so, sometimes two. Really depends on the specific situation, but they are remarkably accurate for a 3D printed part. And on the next slide, you can see what they look like outside of the master collet. So that's a set of blanks that I produced for myself. And I pop those into that master collet, lock them in place with a couple little clamps, and there's a little dovetail interface on the side there. It's a little tricky to see, but it's quite detailed, and it would be very difficult to produce that feature with other additive methods that aren't resin based. And resin printing in this case is not a very good solution, at least for the extended run times that I'm looking at. I could see it potentially working in certain situations, but for me, I prefer SLS. I prefer the workflow of it. I don't really like working with resin personally. And I like the strength and the durability of the nylon here. So another advantage, as it shows on the slide, is the nylon collet pads don't mark your parts. So when you're using a steel collet of any kind, whether it's got insertable pads or it's just a solid steel collet or even a machinable one that's softer, it's going to leave marks when it clamps. That's kind of one of the things they don't really tell you too much about when you get into these collet checks. They have a lot of benefits, but they will leave some kind of mark on finished surfaces on parts, especially for softer materials. With the nylon, that doesn't happen. Nylon's way softer than any metal you're going to be machining, and even a lot of plastics. But since it's held by that steel master collet, that provides all the backing it needs so that the material is only held in compression, and it stays remarkably rigid, as you saw with that long steel part. It's not as rigid as a steel collet, but that's okay in a lot of situations, and where that's okay, that's where these really shine. Um, so moving on, I also use the printers for a lot of assembly tooling because quite a few of our parts require secondary assembly either after finishing or even just straight out of the machine. So in this case, this part receives two magnets, and this was an early prototype of some fixtures that we made to produce these parts, and it actually didn't work out as well as I'd hoped. This one looks really cool, and the magnet dispensing action actually works quite well. But I found that combining both the press tooling and the magnet dispensing into the same part reduced the flexibility that I had for design changes, and it made it really hard to troubleshoot issues that came up down the line. So we moved on from that towards a separated magnet dispenser. It's on the next slide here. And I am unbelievably happy with how well this came out. It's both really effective and also one of the most satisfying fidget toys I've ever made. And what this does is it just strips these little disc magnets off of a stack and allows you to load them into a separate fixture. We're working with these parts. We're doing, several thousand magnets a month, which sounds like a lot, but it actually goes pretty quick, and it's not so many components that you really need fully automated installation fixtures. You don't need to be combining all these operations until you've scaled up far beyond that. So I find that it's better if you separate out those operations in order to fine tune each one. And eventually, as the volume does scale up, we will start combining them back together in order to streamline things, so that we can assemble these parts much faster. But currently the volume's not there, and that this works quite well. And it's a nice ergonomic solution. And it's really effective at what it does. The nylon in this case makes it a lot more durable. I had FDM printed some simpler magnet dispensers in the past, and we had some issues with them where the layer lines, they were just printed in PLA. They would start to delaminate. They would pick up contaminants from other magnets, just, little bits of iron that were in the area or steel chips or anything. That would start to transfer to the magnets. It would start cracking them. It would scratch the coatings. It would do all kinds of bad stuff that we didn't like. And because of how much more durable the nylon is, we just haven't had those same issues with these SLS printed dispensers. And additionally, it's curved geometry here. There's not a lot of features on it that would be useful, or that would be easy to print. Sorry. If they were printed on an FDM machine, you would need a lot of support material, for example. Those complex curves are pretty challenging. And the design freedom you get with something like this is remarkable. So those FDM prototypes did work briefly, and they were a good proof of concept. And then we took what we learned. We here refers to working with the customer in this case, in order to streamline the process even further and develop a tool that really fit our needs for the process. And then we've done some other stuff with printing as well. So this was one that I came up with actually last week. And it's a chamfer attachment for small parts that screws onto the end of a Dremel tool. So just a normal corded rotary tool. And I've got a little 1/8" carbide end mill, just like you'd use for any other machining application, chucked up in that Dremel. And the two sides of the V in this case are adjustable. Those pins on the bottom side, or those holes on the bottom side of it, can accept dowel pins. And those dowel pins, those holes are spaced at a different center distance. So you can select which hole the dowel pin goes into to change the spacing of that V within a certain size range. And that allows you to adjust the chamfer size that this tool produces, because you drop the part into that V, and the spacing of those two guides determines how far down that edge sits relative to the tool. Then you just slide it across, zips the burr off, and you're done. In this specific case, the part that I'm holding there in the bottom left photo, those edges were difficult to hit in process. That part was otherwise done in one operation in the lathe. But when I was holding it in the sub spindle, it was really hard to clock the rotation accurately enough that a fine chamfer would come out evenly across that whole edge. Even like a quarter to half a degree of misalignment there during the transfer, if anything slipped, it would be out of alignment, and you could immediately see it. And that's just not acceptable for these parts. So I printed this up instead, and the total amount of time I spent designing and building this over a couple of iterations was likely less than it would have taken me just to get that edge dialed in the machine, because it was really finicky in this case. So following that, we've got a little bit about the design process of this tool and just kind of the general process I use when I'm approaching these types of challenges. So oftentimes I'll start off with an FDM prototype, and in this case, it was relatively well suited to the task at hand. But we found that the PLA that I printed it in wore out way too quickly. And part of that was because the grooved lands on those surfaces were a little bit too narrow, so it increased the stress concentrations and made it easier for the parts to wear off those, or basically the peaks of those bumps on there that collect grit and help guide the part down towards the tool. So I went from there. I'm like, well, I need something that wears a lot slower. So I took some dowel pins off the shelf and just popped them into some grooves on an initial SLS prototype. And SLS in this case enabled me to get that complex geometry where it was a partial hole with sharp edges inset into the surface at a weird angle. FDM wouldn't do that very well. It's possible, I guess, but it's not likely to give you good results, and it's very unlikely that those pins would have sat in the same plane. But when I printed it on the fuses, it actually worked great. I didn't really like how many pins it consumed in that process. So I decided to see if it would work well with just the nylon faces, considering nylon tends to be a lot more wear resistant than most plastics you're printing on an FDM printer. Of course, you can run nylon on a lot of those, but I generally limit it to PLA for FDM purposes. So I found that the final iteration of this with just the nylon faces, it actually worked great. I ran several hundred parts through that and noticed basically no wear on those surfaces. The chamfers were visually indistinguishable from the start to the end of it. And you know, it cost all said and done, it cost about $50 to iterate through these tools. And throughout the entire process, I had functional tools the entire time. So I was able to actually make headway on the parts while iterating and improving things. So I'd get one prototype done and I'd test it out. And usually while I was testing, I'd already have some ideas for the next version of it. Those would go into the printer while I was using the first version. And as soon as they were done, I'd switch over to the next one, see how it worked, and make some adjustments. And the speed of the Fuse 1 Plus in that case is really remarkable for that, because basically any build that I run is done in like 12, 13 hours. So I can pretty easily have parts in hand by the next day at the absolute latest. Takes 10, 15 minutes to unpack and blast a handful of parts, and you're good to go. And they're so accurate that I don't have to think about allowances for clearance on off-the-shelf hardware. So when I'm using dowel pins, I just model things true to size, and they just fit. Don't really have to worry about it. And I've found that, especially since I'm a turning only shop, I don't have a milling machine in here. And that is very unusual for machine shops, I would say. Most shops have at least some kind of tool room capabilities. They've got a small vertical mill of some kind, or even a Bridgeport hanging around in the back to make modifications to things, to make custom fixtures, all the things that I've talked about here. But I've been able to replace a large majority of what a tool room would do for me with these fuses. Obviously, there's some stuff that does still need to be metal, but if you get really creative with it, you can get incredibly good results out of off-the-shelf precision hardware like dowel pins when used in conjunction with these 3D prints. So Juliet, I'll hand it back over to you.
All right. Thanks a lot, Brad. Thanks a lot for sharing all of this. This is really interesting and great photos and videos. I just mentioned before that we will have also a white paper that comes out with the case study from Brad and the photo as well. So you will have a follow-up with this white paper if you prefer the written version. And we just want to close with a last question to know a bit like what's your impression on the presentation and about 3D printing. And then we can move to the Q&A question. All right. So I'm going to end the poll. All right, so let's move to Q&A. So as I mentioned before, you can use the Q&A button that is appearing in the Zoom. If you have any question, please don't use the chat. I think I've seen a few things written in the chat, but I might miss them. So yeah, you can just ask all your question in the Q&A. Good, so let me start. I will look for the most vote. All right, so first question at Joel is asking, what do you think is the best for material that need to be exposed to big temperatures? So in general, so I'm just going to take this question. I guess it's regarding the 3D printing technology. So if, for example, you are looking into welding, so a very high temperature, then SLA will be better because we have material that is called rigid 10K resin and is really good for high temperature resistance. So most of our case study with welding fixture are actually reported with rigid 10K material. We do have some users that are doing some welding fixture with SLS as well and with nylon 12, but usually it's lower temperature welding. So, and as a note, we're also going to have a webinar about welding next month. So if you're interested, you can also be on lookout for that. And if your application is something else than welding, but just like high temperature, still rigid 10K is really a good solution. With SLS, you still have nylon. I still have fairly good temperature resistance, but it cannot really go very high. Maybe Brad, do you have any experience with like high temperature usage? I don't think you've been using too many high temperature fixture, right?
Yeah, not too much. I've done a little bit of sheet metal forming, but nothing that actually gets significantly hot. I will say that nylon does handle slightly elevated temperatures, at least pretty well. Like up until, water boils kind of thing, maybe a little bit hotter maybe. It doesn't deflect under high temperatures very readily, which is nice. So you don't start to get that softening until it gets pretty elevated.
Good. Good. Yeah, we also had some cases of users that have been printing with nylon 12 some robot grippers that actually pick up hot metal inserts. And this goes maybe to like 80 degrees C, something like that. So it's already quite fairly hot. Yeah. All right, thanks, Brad. So let's move to the next question. How do you deal with warping of SLA print? We've been getting into rapid prototyping low pressure mold in the high temp resin, but we get varying results in regard to warping and often find it necessary to post-process machine the tool. Yes, so for mold, printing mold, I will recommend printing again with rigid 10K, so SLA rigid 10K. We have actually a lot of users that have been pretty successful with that. And to limit the warping, there's a few tricks that you can do. So first, the printer orientation can influence that. So we recommend printing it flat on the wheel platform, not with support. So support will increase the warping. Then another method can be to actually clamp the tool while curing, while you're doing the UV curing. This is also something that some users have done. And then the last thing is also to kind of waiting the UV time. So we recommend a certain UV time to get the maximum ADHD, so heat deflection temperature. But the UV curing is also what increases the warping. So if for you, you see that there's really a big warping, then I will recommend decreasing the curing time, the UV curing time. So those are some tips that I recommend. And yeah, high temp resin warps quite a lot. So rigid 10K warps less. So that will be already a good switch that I will recommend. And just to finish on that, if you're looking for low pressure molds, we have a lot of content about injection molding, short run injection molding with rigid 10K on our website. So I would also recommend having a look at that. All right, next question. What software do you use for instant 3D printed part quoting? That's I guess you are asking that as if we are service provider of 3D printed parts. I guess that's the question. So we are a manufacturer of 3D printer. So if I understood correctly the question.
Yeah, I do actually use instant quoting software, but I'm not that happy with it actually, so I'm not going to say their name live on here.
Okay.
But
All right.
there are several options available.
Okay. Question for you, Brad. Any swelling of the nylon 12 with coolant contact? Any other long-term effect?
So I haven't seen any dimensional change from it. I've soaked parts in coolant for, days at a time, kind of thing. The reputation that nylon has for moisture absorption is mostly related to nylons in like the nylon 6 family. They tend to be a lot more hygroscopic. They'll change size like within the span of a day, kind of a thing. And they'll soak up oils, they'll soak up water, they'll soak up whatever you throw at it. But nylon 12 doesn't really seem to do that too much, and that's part of why I like it for this application. Because a lot of other thermoplastics either get degraded in coolant contact. So PLA is a big one there. It just kind of crumbles over time. Or they swell up from the moisture because it's a water soluble oil. And neither of those are very good for this type of application. So the nylon 12 is actually an excellent fit here.
Yeah, exactly. Actually, it also answers the next question of someone asking, why would you go for SLS over SLA? Really, for anything that is going inside a CNC machine and is in contact with coolant, it should be done with nylon 12 or SLS and nylon powder. Usually our SLA resin doesn't react super well in the long term with cooling solvent. All right, pros versus cons for SLA versus SLS. So maybe we've already just talked about that, but maybe I can just summarize quickly what I would recommend. So again, if you do anything inside machining, use SLS just for exposure to solvent. If you do anything that is like very high temperature, like welding fixture, or that is like in need of a special property, we have a much broader material library in our SLA. So we have some ESD safe, we have some silicone material. So that would be like how to choose will be like one direction, looking into material properties. And then SLS will be more for a high volume of production and SLA for lower volume of production. So that will be like the two main choices. In general, I don't know what's your impression, Brad. Have you actually printed with SLA before?
Yeah, I actually had a few Form 2 printers for a little while, and I've tried most of the resins that Formlabs offers up until probably about a year ago. I was holding on to the printers for a friend of mine that didn't have a place to use them at the time. So I got to just kind of experiment for a bit, and that was before I had the fuses.
Mm-hmm.
Um, so I did print some small drill jigs and stuff with the Form 2s in rigid 10K, I believe, and they worked reasonably well. They were definitely it was definitely a different experience than working with the nylon. The main thing I don't like about resin printing is how everything gets sticky, even if you try really hard to keep it clean. Everything in that workspace will get covered with resin eventually. And that's just kind of the way it goes. With SLS, you've got dust control to deal with instead. Um, but I think both have their places in a manufacturing environment for sure.
Mm-hmm. Yeah, definitely. I think that's a good conclusion. We have some users that really have only one application and they know exactly which one to use. But then if you are in a shop in a manufacturing environment, you might really find application for both of them, and they will be quite useful for both. Yeah. All right. Maybe Brad, you want to answer about that, but did you see any barrier with starting with SLS compared to FDM and SLA?
So the big thing is going to be cost, of course. It is a lot more expensive to get into SLS versus SLA or FDM. Um, the prices are, of course, on the Formlabs website, but it's about an order of magnitude difference. So it's not small.
Mhm.
Um, for my specific use case, it wouldn't make sense for me to have a fuse exclusively to print the jigs and fixtures that I'm making. The reason I can justify that is because my business also includes like job shop type print service work, basically, and also stuff for my own internal products that I sell to a niche hobby market. Um, so because I'm already using the printers in ways that are quite productive for the business, their flexibility and the fact that I can just throw random parts in a build without having to change anything about my process means that I can just pop these little tools in there as needed, and it's really convenient. Um, but it would be a lot harder for it for me to make it make sense to just buy the fuses on their own for this same purpose.
Mhm. Okay, thank you. What 3D printer is best for milling? I don't know if you mentioned, have you tried milling? No, you don't have a milling.
So I have done milling in the past. We were previously doing more like prototype work, just with a 3-axis and then a 5-axis mill. Um, and I've used the fuses for some fixturing work for that, not a whole lot. But with any kind of plastic work holding, you got to keep in mind the forces that it's going to see. So you're not necessarily going to replace metal clamping components in every possible application. So aluminum soft jaws, for example, are the standard for um, vise work in a milling machine. And in many cases, you can replace them with plastic jaws that are printed, and then often you're going to want to skim cut it in place for the same reason I skim cut the collet pads in the lathe, and that's to ensure the alignment relative to the machine and to ensure that the geometry of whatever pockets machined in there is what you expect. Um, that said, I have also printed small inserts on the fuses that just get clamped in a regular vise, and they're shaped so that it fits existing geometry on the part. But because I was running those in a 5-axis mill with probing and everything, I could account for small geometric errors and tolerance stack up that happen when you throw a part that was made in an entirely different process into a machine, um, basically blindly. Um, So I would say that the fuses, at least out of the Formlabs line, are definitely your best option for printing milling fixtures. I've seen people do it with FDM printers too. Those you definitely have to post machine in place if you're planning on having any kind of accurate location. Um, but yeah, I would definitely lean towards SLS for that.
Okay, thank you. We had a few questions on that, so I just answered them. Have you designed SLA fixture in multiple pieces? And if so, what is your preferred method to join them? Hardware, adhesive? Yeah, it
Good
happens.
question.
Yeah, I mean, have you done that, Brad? Or
Yeah,
yeah.
yeah. So for example, the magnet installation tool is multiple components, so it's three separate parts, and in its case, I use just off-the-shelf dowel pins as the fasteners, so there's no screws or anything in it, and I can actually print the press fits for the pins into the parts. There's no real difficulty in doing that, and it's very reliable. So you just pop them in with finger pressure, and they stay. Um, you can also print threads directly into parts if you're using fasteners. You can tap it just like you would any other plastic. Self-tapping screws work great. Um, Super glue actually works remarkably well on it. I think that's because the skin of the prints is slightly porous, so it kind of wicks into there and grabs really nicely. So the magnet that I used in the magnet dispenser to attract the stack forward and make it work is just super glued into the end there. It's a close fit in the pocket, but the little bit of glue really helps with the reliability and retention there.
Okay. Yeah, and both our SLS and SLA part can be post-processed with, like, they can be milled or they can be paint coated. We actually have an article about post-processing technique for both SLS and SLA. So if you're curious to see what can be done, there's really a lot of different things that can be done. So what did you, okay, we've answered that already. Nylon 12 over rigid 10K. Why choose SLA? What choose SLS over MGF? I don't know if something that you've, someone is typing.
Yeah, so I chose SLS over MJF primarily because of cost. With MJF, you're locked into HP's ecosystem and it's very, very expensive. Like the fuses are about an order of magnitude more expensive than the Form series, for example, and MJF is about an order of magnitude more expensive to get into than the fuses.
Mhm.
So pretty tremendous difference in cost there. And I'm not a service bureau like that. I'm not trying to take a significant portion of that market. It just isn't reasonable for what I'm doing right now.
Okay, perfect. Thanks. So one question, I guess, for me, do you know what Formlabs roadmap is in the future is for the material library? So I cannot really share anything for the material roadmap, but for sure it's like a big part of our R&D is to develop new materials. So this is something that we are working on constantly. And we actually really appreciate feedback and feedback on what new material is needed and what are the things that are lacking in our product offering today. So really happy if anybody has some suggestions, some feedback to share. That's really something that we pay attention to. Okay, so that we answered. And oops, sorry. So someone asking to recommend what SLA resin would you recommend for similar use case to Brad? So I guess for turning fixture. So as we mentioned before, SLA resin will be quite difficult to use with inside a turning machine because of the cooling solvent. So I will actually not recommend using SLA resin inside a turning machine. I don't know if you've used that, if you tried it at all, Brad, to try SLA fixture inside.
No, I actually haven't had SLA printers since I got this lathe. But I would expect that for short run stuff, like something like a rigid 10K could work pretty well.
Mm.
As long as it's not going to be in there for, tens or hundreds of hours. Like if you're doing quick turn prototype work where you need a one-off, then it'll probably be all right. But again, I haven't experienced the chemical compatibility side of things with that very much.
Yeah. Yeah, that's the thing is like nylon is like pure nylon that is like really resistant to coolant, while resins are a bit less resistant. But in general, for tooling, rigid 10K, I would say, as you mentioned, is a good default material because it's very rigid and it has high thermal resistance, so it can really handle a lot of stress, basically. So that would be a good choice. And it's also a resin that you can use for multiple uses. All right, then we went through all the questions. So I think this is time to wrap up. So thanks everyone for joining, and thank you, Brad, for your participation. This was really interesting cases to see. And again, for everyone who joined today, we will have a white paper version of this case study with even more cases in there. Thanks again, and have a good day, everyone.